Hello everyone. Today I will teach you the example illustrating Vout as function of time. This Vout is of transistor which is acting as a sampling switch under the name analog building block. So this is already the case which we have taken in the last lecture, that Vn is equals to 0. This is the clock pulse applied at the gate terminal, and this is V out, and this is Ch, which is the sampling capacitor. Okay, this is initially charged to the value VDD. So let us draw and illustrate whether this particular transistor is in saturation or it is in triode region. So we can see that source is at lower potential in case of NMOS than drain terminal. So this is the source terminal. This particular is the source terminal. This particular is the drain terminal. And we can see that V out, V out, right, which is the VDS voltage, V out is greater than VDD minus VTH is greater than VGS minus VTH. So we can say M1 is in saturation mode. Okay, M1 is in saturation mode. Following this condition, we can write down as V out can be written as VDD minus the current flowing in this particular transistor, VDD minus the voltage drop. The voltage drop is ID1 T by CH. You can say that from where this occur, Q is equals to CV, we can say V is equals to Q by C. Q can be written as IT by C. Okay, so let's take a condition after T1 time. We know when it is fully charged to the value VDD, that is the time constant RC. After this time RC, this what is this T1 time RC? It can be written as R is simply the voltage upon the current. This is the VTH, and this current is the current due to saturation region. So we can write T1 is equals to RC is equals to 2 VTH by CH into CH mu and cox W by L VDD minus VTH. Okay, after this time, after this particular time, what happened? M1 enters the triode region. M1 enters the triode region. It yield a time dependent current. It will yield a time dependent current. Okay, and we can write CH dV out by dt is equals to the current. Minus sign indicates that the current flows in this direction from drain to source. Okay, so it can be written as, we know in the triode region the current is half mu n cox W by L 2 VDD minus VTH V out minus V out whole square. This time is greater than time t1. Okay, we can rearrange these terms and write it down as dv out by 2 vdd minus vth minus v out equals to half mu n cox w by l dt upon ch. Okay, upon partial fraction of this term, we get 1 by v out minus vdd 2 vdd minus vth minus v out dv out upon vdd minus vth. and this term is same. Now integrating, we get ln natural logarithm of the term multiplying this side having a minus sign, mu n cox by ch w by l t minus t1. Okay, integrating from time t to t1, we finally get ln v out. Solving this particular equation, now taking the exponential of both sides and solving for v out, we get v out is equals to 2 vdd minus vth exponential minus vdd minus vth mu n cox w by l ch t minus t1 upon 1 plus exponential minus sign vdd minus vth mu n cox ch w by l t minus t1. Okay, in another case we will see that how this v out works. Let's see. Okay, this is also the case we have taken when v in is 1 volt, or we can say when v is you can say vdd. In this case, let's see which is the triode region, which is the drain region. So in this case, the drain region is this one and source region is this one, because drain is at higher potential, source is at lower potential given 0 volt. Okay, in this case, the drain and gate terminal both are at VDD, both are at same potential. Then this transistor is in saturation, taking the current for saturation mode as ID1 is equals to Ch dV out by dt, and it can be written as again the same equation for the saturation region, VDD minus V out minus VTH whole square. This is again the voltage VGS. You know, VG K terminal is this. VG is equals to VDD, and V out is this one, this VS. Okay, VGS is VDD minus V out. In this, channel length modulation is neglected. It follows that dV out by VDD minus V out minus VTH whole square is equals to half mu n cox W by L dt. Okay, and what we do, we integrate both the side, integrating from 0 to V out half mu n cox ch W by L t, integrating from 0 to t, where body effect is neglected, V out can be assumed as 0. Thus, we can get V out is equals to VDD minus VTH minus half mu n cox W by L to ch t plus 1 upon VDD minus VTH. So this is the equation of V out in terms of T. Okay, in terms of T. Okay, we can say that if T tends to infinity, V out tends to VDD minus VTH. Okay, as V out approaches VDD minus VTH, the overdrive voltage of M1 vanishes, reducing the current available for charging CH to negligible values. So for VDD minus VTH, for V out to be VDD minus VTH, the transistor conducts some subthreshold current, and given enough time to bring V out to VDD. Okay, so let's take another case. The serious limitation of this MOS transistor is that if the input signal level is close to VDD, then output provided by NMOS switch cannot track the input, which is necessary for a MOS transistor to work as a sampling switch. Okay, and secondly, the on register of the switch increases considerably as the input and output voltage approaches VDD minus VTH. So it will leave very small current for charging capacitor. Okay, so this is the this both of them are serious limitation on the MOS sampling switch. So input signal should not be close to VDD, and the on resistance of the switch increases as the input and output values approaches VDD minus VTH. Okay, so this is all. Thank you.